This is Unit 8, Video 3. In this video we will talk about temperature and pressure effects on solutions. Remember, this whole chapter is over solution chemistry. And first we'll talk about the temperature affecting the solubility of a solid in a liquid. Now, as temperature increases, the solubility of a solid will also increase. Let's draw a little up arrow here. And this usually is pretty self-explanatory. What we have here is the brewing of tea. Some of you that enjoy some hot tea in the morning may realize that the solid inside this tea bag is what's being dissolved. And you brew tea at a hot temperature and then you cool it down to your appropriate desired temp. And so a solid is more soluble when hot. That's the idea. Now here is a solubility curve graph, and it lists a bunch of ionic compounds. Notice all of these compounds here are ionic. Sodium nitrate, calcium chloride, lead nitrate, potassium nitrate, so forth. These are all ionic. Now, if you remember, ionic compounds were always solids at room temperature. So all of these, in fact, are solids. And you see, as we increase the temperature, as the temperature goes up, most of these will increase in solubility. Interestingly, some of them, the relationship is linear, like in the case of potassium nitrate. In the case of sodium chloride, notice it's just barely increasing. At the freezing point versus the boiling point of water, you can barely just dissolve another 6 grams or so of table salt, which is also very interesting. So some are linear like this. Others, like calcium chloride, are exponential. They just shoot up in solubility. And that is due to factors like ionic charge and intermolecular forces, how strong those are with water. It's usually water molecules that are responsible. Now, some of them, rarely, like cerium sulfate, the solubility actually decreases. This is an interesting idea, but most of them will be increasing. This is actually also due to that idea called entropy. That will help explain why eventually when you get to learning about it. So in general, though, the solubility of a solid in a liquid increases with temperature. Now, the solubility of a gas in a liquid actually decreases. So as temp goes up, solubility of a gas actually goes down. So this is the opposite of a solid, and this is because gases are technically, if you put more energy into water, what happens is the gas has more energy to boil off, if you would. You're putting more energy into it, so the intermolecular forces allow the gas that was dissolved in here to essentially break those intermolecular forces. The intermolecular forces are weak to begin with because most gases are nonpolar. These here, most of them are nonpolar, and so temperature causes a decrease in the solubility. So you see curves going down. Now, also dependent on, some of them are more flat, others less so. And this is actually an important concept in allowing little critters that live underwater, whether animals or plants, to survive. If you increase the temperature, the solubility of a gas decreases, and fish and other forms of life depend on dissolved CO2 if it's a plant-based organism or algae, and animals depend on dissolved oxygen in the water, which there's not a lot of it, but enough for them to do well. So when you increase the temp, these come out of solution, decrease in their solubility, and that's why that's a problem called thermal pollution. Another example of this would be, this is why if you want your soft drink, this is a soft drink, after you've opened it up, if you want it to remain more fizzy, if you want it to retain dissolved carbon dioxide in there, you would put it in the freezer or in the fridge. If you put it in the freezer, that may cause other problems. Put it in the fridge, the decreased temperature will allow the gas to be soluble for a longer period of time. So this is the opposite of solids. Now, pressure also has an effect, and it has an effect on the solubility of gases. So as pressure increases, the solubility of a gas in a liquid increases. So you don't want to increase temperature, but you want to increase pressure to dissolve a gas. And this is simply because as you increase the pressure, you're essentially causing more gas molecules to contact the liquid and go into the liquid. That's really all you're doing. So the more gas particles there are at the surface, more of them could go into the liquid, form bonds with the water, and essentially you're holding them there. Now, if you release the pressure, like usually happens when you open up a fresh bottle of soda. What happens is those gas bubbles suddenly release. If you do it like slowly and carefully, a few of them release, and then eventually intermolecular forces, as it gets heated up, those intermolecular forces get weakened, and or rather there's more energy, and the gas escapes eventually. But you can actually reverse the process if you buy one of these. This is a fizz pump. You can actually pump up your soda after you've done drinking it, and you can pump it back up to a certain pressure, and that'll keep the fizz from escaping. This is actually more effective than cooling it, because increasing pressure really has a pretty good effect on gases. Now there is a law, it's called Henry's law, that we won't do too much with, but it's essentially a direct relationship. The higher the pressure, the higher the solubility of the gas via Henry's law. It says S times some sort of constant, and then times pressure, like that. Usually throw a constant, it's a direct relationship. The higher the pressure, the higher the solubility. It's pretty direct. So, and here we say that pressure has no appreciable effect on the solubility of a solid in a liquid. So solids don't really get affected by increasing pressure. That's the idea. Now when we say solubility, what we mean is how much solute is needed to form a saturated solution. So saturated, remember, means full. It cannot handle any more at a given temperature. So that's how we define. We haven't really defined solubility yet, but this solubility means a saturated solution has been created at some sort of temperature, because as we've seen, temperature has a big effect on the solubility of whether you have a solid or a gas. So in the case of sugar, sugar is a solid, and the solubility of sugar at 20 Celsius, roughly room temperature, a little cooler, is about 204 grams. At the boiling point, it's almost 3 times as much, 400, rather almost more than 2 times as much, 2.5 times, 487, which is pretty important. We see it's a pretty big effect. So the solubility, this is a solid in water, and this is for 100 grams of water. So you can actually dissolve, strangely enough, 5 times more sugar in water at the boiling point than there is water. And here is that same heating curve table that we've seen. We're going to ask some questions about it. Now, what I should say to begin with is the point at which, so pick a point anywhere. We'll say, let's pick good old NaCl, sodium chloride. So if you go up to about 30 Celsius, here we are, 30 degrees Celsius. So at 30 Celsius, you can dissolve about 35 grams of salt in water. So that's pretty good, 35 grams of regular salt in water. And so this is the limit of the solubility. This would be a saturated solution. At this point, you've got yourself a saturated solution, which means if you're at a point above that, then if you want to try to put 40 grams, you want to put 40 grams into water, well, 5 of the grams won't dissolve. 40 grams would be a saturated solution. Now, if you try to put 30 grams, that would be an unsaturated solution. So another 5 grams can go into the solution. So below the line is unsaturated. Above the line, technically, is saturated. Beginning with that point. So bearing that in mind, we can actually take a look at some questions, and the questions will ask essentially us about this graph. So question 3 says, looking at the solubility curve, will 50 grams of the following be saturated or unsaturated at 45 Celsius? We're looking for potassium chloride and potassium nitrate. So we're looking at 50 grams at 45. So let's find our 2 compounds, potassium chloride and potassium nitrate, these 2. So at 45 Celsius, so we are looking at this point right here, and we're saying we're putting 50 grams into it. I'm sorry, 45 degrees Celsius. No, we're looking at 45 Celsius. There it is, right here. We're putting 50 grams, so we're looking at this point. All right, 45 Celsius, 50 grams. So at 45 Celsius, potassium chloride, it looks like can handle about 41 grams or so. Now, if we're putting 50 grams, we're putting this much in, then potassium chloride will be saturated, because its saturation point happens at around 41, right here, 41 grams. So this one will be saturated. Whereas potassium nitrate, at that temperature, it can handle quite a bit. It can actually handle about 75 grams. So if we're only putting 50 grams in, that's all we're putting in, 50 grams, this guy will be unsaturated. So hopefully that makes sense. So we can actually answer potassium nitrate would be unsaturated. Oops. And the other one would be saturated. So sat and unsat. Now, what's interesting about this is that potassium nitrate, the nitrate, is actually very soluble. Nitrate is actually able to form hydrogen bonds with water. Nitrate looks like this. The little structure of nitrate looks like this. Now water, remember, has H2O, which has hydrogen bonding. So this really electronegative oxygen can actually hydrogen bond with the hydrogen version, or a hydrogen portion of water. So it can actually form strong hydrogen bonds. That's why potassium nitrate is really soluble in water. This nitrate business makes it very soluble. So, because it's got that oxygen that can participate in hydrogen bonding. One more question. This one says, looking at the same curve, how much KClO3, potassium chlorate, can be recovered from a supersaturated solution at 70 if it's cooled to 30? So, if we dissolve everything that we can at 70 degrees Celsius, so let's think about 70 Celsius for potassium chlorate, and then we're going to cool it down to 30 Celsius. So remember that? Take a look at the graph. So here is potassium chlorate. So we're going from 70 to 30. So we're going from here down to right here. So it turns out that at 70, the solution can hold 30 grams, and at 30, the solution can hold 10 grams. So the difference there is 20 grams. So we can actually pull out 30 grams out of a solution. If you make a solution of potassium chlorate at 70 Celsius, a saturated solution, and then if you cool it, it'll be supersaturated, and slowly you can recover 20 grams. So the difference here is 20 grams, if that makes sense. And that is the answer to the question. 20 grams of KClO3 can be recovered. So hopefully that makes sense. So we've taken a look at the solubility of certain substances at different temperatures. We'll take a look at molarity in the next video.